Everyone, my name is Valentine. So I'm a chemical engineer and also researcher in the biomatter lab. Now, we all probably are aware of the current challenges associated with climate change and global warming. You should know this. We understand the challenges that we face currently as a global community. In response to these challenges, we have sought to explore valorization strategies that seek to encourage transitions from a linear economy to a more circular. In other words, we are seeking to encourage scenarios that facilitate resource recovery as opposed to disposal of waste biomass. Now, to this regard, this particular presentation will explore the biorefinery concept. What is the fundamental of the biorefinery? What motivates the biorefinery concept? Why are we doing it? Right? And also a very quick synopsis of the particular researches that we have undertaken so far in this area. We must understand that the essence of the biorefinery concept is to integrate biomass conversion technologies. You are integrating biomass conversion technology and unit operations to facilitate the deconstruction of biomass. You deconstruct biomass to get the macromolecules, transform those micromolecules and reconstitute them to get high value products. That is the essence. That is what we're trying to do. Now, this particular biorefinery concept essentially seeks to ensure that we are integrating biomass conversion technology in such a way that we can retain economic viability without compromising environmental systems. That is the goal. Now, for the most part, biorefineries may be categorized based on the feedstock or the product type, right? Now, if we're utilizing biomass indeed as a feedstock for the production of energy, we consider such biorefineries as essentially a bioenergy biorefinery. If, on the other hand, we're looking at a biorefinery that is producing targeted biochemicals, we consider those biorefineries as biochemical biorefineries. It's important to also acknowledge that with respect to the classification of biorefineries, they may be classified based on the complexity. For instance, we may have a phase 1, phase 2, or indeed a phase 3 biorefinery that defines a biorefinery that can use one feed waste stream as a feedstock, right, to produce a target product. That will be a phase 1 biorefinery. A phase 2 will have a singular entry feed stream to produce 2 product streams. That is a phase 2 biorefinery. And of course, a phase 3, multiple feed streams entering the biorefinery to produce multiple products, right? We could also categorize biorefineries based on the so-called color coding. For instance, we may have a biorefinery that we call the gold biorefinery, which is essentially a feedstock that is based on the lipids, right? A black biorefinery, which is the insect biorefinery. The marine biorefinery, which is the blue biorefinery. So there are color codes for different kinds of biorefinery that's more or less just introduced for simplicity, right? Now, as I said earlier on, what we are trying to do is we are trying to maximize value extraction without compromising economic viability. That is what we are trying to do, right? So you have the value pyramid. Essentially, we are trying to get the best we can, right? We could easily get energy, we could easily get electricity, but we are trying to get high value products from perceived waste streams, perceived discards, things that we typically dispose, right? Now, to this regard, we have investigated for the first time succinic acid production from waste apple formats. How did we do this? We integrated unit operations of pretreatment, fermentation, and indeed purification, where the fermentation was achieved using the bacterium Actinobacillus succinate, right? This is a facultative anaerobe that is able to convert C5s and C6. So, in other words, pentoses and hexoses into the succinic acids, right? Now, purification in this particular case was achieved using a cascade of distillation columns, right? Such that we were able to employ extractive distillation to recover pure succinic acid. And we must understand that this work was done strictly via simulation studies. So we had to integrate Aspen Plus as a process simulator to more or less simulate the process, right? Every detail that has been employed here has been obtained using experimental data that has been sourced from literature. So we just use those as an input and utilize aspects of the mass balance, energy balance, phase equilibrium balance, as well as define the thermodynamic properties of the chemical species in the vapor and the liquid phase, right? Now, for this particular simulation, we utilize the non-random solid-liquid thermodynamic property to determine the dependence of the phases of the chemical species in both phases, so the relationship between the phases of the chemical species in the liquid and the vapor phase. What we sought to do here was to undergo a techno-economic assessment. So we are trying to describe or establish the technical feasibility as well as the economic viability of the process, right? In this case, we utilize, for our case, the minimum selling price of succinic acid as a suitable economic performance metric, right? And compared alternatively two different strategies for utilizing waste outcomes, in this case, as our feedstock for the valorization process. Now, we have utilized waste outcomes as a feedstock for our biorefinery, largely because of the abundance, right? You see alcohols everywhere. Now, within Europe, you have about 4 million tons of alcohols generated annually, right? Which is quite significant. Right? This waste must be managed. You must find ways to handle the waste, right? Current strategies of managing waste alcohols involve, for the most part, utilizing it as animal feeds and as soil additives. However, we considered such approaches as quite unsustainable, largely because of the high moisture content that characterizes waste alcohols and the acidity level that characterizes this. Of course, we should recognize that when you have a feedstock that is very acidic, you cannot employ it as a feedstock for ruminants, neither can you add it to the soil, because that means you have to introduce some form of lime to get the pH back to more neutral. Right? So what did we do? We essentially compared two pathways. The first pathway tried to produce bioelectricity. So in other words, we utilized the lignin fraction from the waste alcohols as a fuel source, as a solid fuel. So we combusted the lignin fraction, utilized the heat generated from the combustion to facilitate high pressure steam production. After which the steam was now employed in the turning of a turbine, right? And the turbine was used to generate electricity. That was the first half. The second pathway, we looked at a scenario where we utilized everything that wasn't used in the production of succinic acid as a feedstock for producing biogas via anaerobic digestion. Right? So we're able to establish indeed that we could actually produce high value succinic acid at a lower selling price when we're producing biogas as a co-product for the particular biorefinery. So in this case, this will define what we will call a phase 2 biorefinery, right? We also, for the first time, were investigating the potential of producing, for the very first time, one biorefinery that could produce at the same time 3 target products, right? Where we focused at the production of lactic acid, HMF, and xylitol. To do this, we had to integrate unit operations of hydrogenation, dehydration, and indeed fermentation. So in this particular case, we utilized Lactobacillus stacey, right, as the preferred microbe to facilitate the conversion of C5s and C6 sugars, so pentoses and hexoses, right, to lactic acid, right? Now, the lactic acid was produced in a broth, right, so we had to purify it. Now, to do this, we had to first undertake a stepwise alkalination using Ca, that's calcium hydroxide, and of course acid treatment. So we first produced calcium lactate, then we acidified it to get the lactic acid. Right? Hydrogenation was achieved using the high pressure hydrogen to hydrogenate xylose, right, to produce xylitol. And of course, HMF was produced strictly by acidified dehydration of hexose sugars, right? Now, what did we do here? What we did was to establish objective functions. So we were trying to establish objective functions that show the dependence of the economic performance to selected variables within the biorefinery. So we identified 2 objective functions for this particular simulation. The first objective function was the economic objective function. In this case, we utilized the IRR, so the internal rate of return, as a selected metric so that showed the performance economically of the biorefinery. right? The second objective function essentially was the environmental performance objective function. What we utilized the greenhouse gas emissions equivalent, in this case CO2 equivalent per kg of the feed that was fed into the biorefinery as the second objective function. We optimize these objective functions using genetic algorithms to find the best trade-off between the objective functions and determine which biorefinery best satisfies the need to guarantee economic sustainability as well as environmental sustainability. This was our goal. Now we're able to show that it was possible for us to retain economic viability with an IRR which is specified as 0.1, 10%, while also ensuring that the greenhouse gas emissions were better than if you were to dispose of the waste outcomes in landfills, right? So we just compared our results, what you get from literature, essentially. Moving on, we also investigated the potential of utilizing waste outcomes in the production of acrylic acid. Now, to do this, we had two pathways that we compared. We compared the fermentation dehydration pathway and the thermochemical fermentation oxidation pathway. Now, the fermentation dehydration pathway essentially involved the conversion of sugars to lactic acid prior to dehydration to produce acrylic acid. While the thermochemical fermentation oxidation pathway involved the conversion of waste alcohols to syngas, then converting that syngas to ethanol, right? Then dehydrating the ethanol to produce ethylene, then subjecting the ethylene to metathesis reactions to produce propylene, which is then oxidized to produce acrylic acid. We're interested again in this case to demonstrate this prevalent counter effect of economic and environmental performance. We show that we could get the so-called FD process, so the fermentation dehydration process, had better economic performance, right, with respect to the minimum selling price of the acrylic acid, but presented a kind of poorer environmental performance when the potential environmental impacts were considered. Now, you will notice that so far I have focused on the utilization of C5s and C6, so pentoses and hexose sugars, as useful fractions in the biomass that we have employed in this valorization, right? So far, we have employed lignin solely as a solid fuel to produce heat and electricity on site to feed the energy requirements of the plant. Now, this is not considered a sustainable approach, largely because lignin, as far as we know, is established as a potentially rich source of not just aromatics, but also potentially a source of alkenes, right? So in this case, we undertook some form of environmental experimental optimization to optimize the production of aromatics, right? Now, what we did was to undertake a so-called Insitu hydrogenolysis of lignin to facilitate selected depuration of lignin to produce targeted aromatics and targeted alkenes. Now, I won't go into details, but as you know, we don't want our idea discussed too much, right? It's under review now to be considered to be patented, right? But the core deal here is that we were able to demonstrate that you can get alkenes, high-value alkenes, and targeted aromatics from waste outcomes, high-value aromatics, by introducing what we call the Insitu hydrogenolysis, selective depuration of lignin for this particular case. Now, some discussions regarding this idea are presented in this review paper that we published recently. Some results have also been presented, of course, in the limits of our intellectual property. Going forward, we very quite recently, our students were able to demonstrate the potential of utilizing subcritical water in the production of polyphenol, right? She was able to show that if you were to utilize subcritical water, you had the potential of increasing the yield of polyphenol extraction by up to 3-fold. Now, this is in comparison to the utilization of using ethanol water mixtures. So I was interested. It got me thinking. Now, if we were to scale up this process, what is the energetic penalty of utilizing subcritical water in the extraction of said polyphenols? Does the energetic penalty exceed the potential benefits of the high yield of these polyphenols? Can we truly say that utilization of subcritical water is indeed better than utilization of ethanol water mixtures, right? How do we do this? We had to use what we call the so-called phase 2 biorefinery, where we were looking at the potential of using waste alcohol as the production of polyphenols using solvents, right? In this case, ethanol and water. And in another case, we're using the polyphenols or the waste alcohol and producing polyphenols using subcritical water. Now, why not just put the waste alcohols and put them into an anaerobic digester and get biogas? Why go through this process of trying to extract polyphenols for sale? That considered the third particular scenario that we are concerned about, utilizing the waste alcohols in the production of biogas as a fuel for our combined heat and power plant to produce steam and electricity. So this provided for us three case scenarios that I am currently undergoing some form of investigation by simulation studies. It's our belief that based on this comparison, we'll be able to establish if industrially it makes sense to actually undertake some form of subcritical treatment, or perhaps we just dump it into an anaerobic plant and move on. Beyond these particular studies that I've discussed, we must also acknowledge that within our lab, we have students that are undertaking, as you may have heard earlier, valorization of insect-based biomass. So in other words, the insect-based biorefinery, so the black biorefinery. We also have students that are undertaking the utilization of marine-based biomass to produce selected collagen. So in other words, the blue biorefinery. Right, this biorefinery essentially indicates the commitment that we have within our lab to push solutions that are relevant to real-life scenarios and real-life problems that face us globally: greenhouse gas emissions, right, climate change, and indeed blue warming. So thank you for listening. Now, before we go, I'd like to encourage us to please have a look at the YouTube channel and see some simulation biomass lectures for beginners. Subscribe and share. Thank you very much for listening.